Hi everyone, my name is John Dunn. I'm head of AWR training. Our new series of Jumpstart videos is designed to get you going quickly. So without further ado, why don't we get started? What we're going to do in this video is take you on a quick tour of the Microwave Office software. And in particular, I'd like to show you today something we call the Microwave Office design flow. What you see in this schematic is essentially the design flow in Microwave Office. And we're going to go ahead and get started here in the upper left-hand corner. The first thing you would do, of course, is normally draw a schematic. And then we're going to make graphs. And we put measurements on the graphs. The measurements, as we'll see, will actually control all of the simulation. I would like to point out this actually is very different than other software you might be used to, where a lot of the control is driven in the schematic. We, on the other hand, like to control everything in the measurements, believing it actually has some useful benefits. Welcome to Microwave Office. Of course, this project has nothing in it at the present time, so let's start a new project. If you follow my cursor up here to the upper left, I'm going to go File, New with Library, and I'm going to use one of these example libraries. You see 3 of them before you. They ship with the software and you're free to use them. MESFET is a mimic process. Module is a board process. That is the one we're going to use in this video. And GenBIC is a silicon process. So I go ahead and click on AWR module, and it appears nothing has happened. Well, a lot has gone on behind the scenes. In particular, if we start over here on the left in the project browser, and the project browser is the brains of the project. It's where all our project options are, our schematics are going to go, our graphs are going to go, optimizer and yield goals, EM projects. I'm going to double click here on project options. And the first thing that we face is the frequencies, and let's go ahead and set the frequencies from 1 to 10 gigahertz in steps of 0.1. Now it's very important you hit the apply key to carry out the action. This is the only time in the software you need to do this, and it's a common cause of user error. If you did it correctly, you should see the frequencies here in the left window, which I'm now scrolling through. The reason we make you hit the apply key is it, quite frankly, protects you a little bit, because if you change all the frequencies, you, of course, will change the entire project. Now, the next thing I'm going to do is show you global units. And the global units came in with the library. And what most people worry about are the frequency here on the left, which for us is in gigahertz, and down here on the lower right, the units, which in this case are in millimeters. I highly recommend that you don't go changing your units in the middle of a project. The software can handle this, but your nice round numbers that you have for your widths and lengths, etc., will of course become rather ugly looking. I'm going to hit the OK key, then we're ready to go. Well, what else did the library bring in besides units? Well, if we go down here to the bottom, you'll notice there's 2 other browsers, the Elements browser and the Layout browser. And I'm going to start with the Elements browser. What you see before you are all the built-in elements in the software. The trick, of course, is to know where they are, and we'll get to that in a minute. You'll also notice this Libraries tab. If I click on that, you see 2 libraries. AWR Website, and in AWR Website, if you click on that, what it does is it goes out to our website, and we have a lot of various vendor libraries. And so, for example, if I go here, Parts by Vendor, you can see, for example, under Coilcraft, we have various Coilcraft inductors, etc. These libraries, we work with the vendors on them. They are free public domain libraries. There also, of course, are other libraries, pay-for libraries, proprietary libraries, if you so wish to inquire. When we brought in the library, it also brought in its own library, and in particular, it's this AWR module. And if I click on that, you will see there are a variety of components. For example, under capacitors, you see 3 capacitors, which are chip caps. These have a model. Quite frankly, in this library, they're just a simple cap. Normally, you would have a more sophisticated RF model or perhaps an S parameter file. They also have layout, and they might even have documentation. It's relatively easy to make your own library if you wish to do so, although it's outside the scope of this particular training. The final thing you may wonder about is the system blocks at the bottom here. These are model elements for our VSS system simulator. I can show you that quickly, and you'll notice there are things like coding, mapping, communication standards, all the sorts of RF system things you would expect in a system simulator. Not our topic today. It is another product called VSS. The final tab, if we go back down to the bottom, is the Layout tab, which is pretty boring right now. When we get to Layout later in this video, in the lower left box here, there will be the various drawing layers that we can use. And up here at the left will be various cell libraries, if we have them. This particular library actually did have one cell library with a couple layout cells in it. At this point, I'd like to make the schematic, and what we can do is go over here to the left on the project browser, Circuit Schematics, right-click, New Schematic. Notice instantly one of the advantages of our software is love it or hate it. One thing that Microsoft has done is pretty much standardized hotkeys and the look and feel of mice. We, of course, have a 2-button mouse. I highly recommend you have a wheel on that mouse, especially in layout. Left mouse button selects, right mouse button brings up menus. When we talk about hotkeys, standard built-in hotkeys, Control-C for copy, Control-V for paste, and my favorite key, Control-Z for undo. I click on New Schematic, and I'm going to name it my space stub. Now, you can put a space in your schematic names. Virtually anything in the project can have a space. For things that the outside world will see, like the name of the project itself, or perhaps drawing layer names, if you're shipping them out to another layout tool, I highly recommend you maybe use an underscore and not a space, since many software products and operating systems out there will get confused. So we're going to leave the space in. My stub, and you see a schematic, and of course there is nothing in the schematic. So at this point, let's go ahead and start drawing our simple little circuit. I go down to the lower left to the Elements browser, and when we look at these elements, as I mentioned before, the biggest problem is where do you find things? First of all, we break the elements up into 4 main groups. There is microstrip, which is what we're going to use, strip line, and coplanar. And in addition, the 4th group is ideal elements. So, for example, under transmission lines, you would have various ideal type transmission lines that you could use. I go to the microstrip category and hit the plus button. You can see we have bends and junctions and coupled lines and lines. We're going to go to lines here, and you will notice there are a lot of microstrip lines, and of course the question now before us is which one to use. Incidentally, as an aside, you'll notice each element has a description of it, which is what I like to have my setting for. If I right-click in this field, notice you also could, for example, have small icons, which is the default. Unfortunately, when you use that, you have no description of what the lines are, so I prefer details. We're actually going to use here an emlyn, which I just selected. But why so many lines? Well, there are 2 reasons for that. First of all, you might have a number of layers in your substrate. The emlyn, which we're going to use, is for 1 layer with a perfect conductor underneath, the line on top of that layer, and air above. Maybe you want to include solder mask, so then of course you would need 2 layers, your dielectric, your solder mask layer, and air above. You couldn't use emlyn. The other reason we have so many different line types is how they're calculated. This particular one we're going to use is called a closed form model, as you can see here in the description. And if you look at the manual help on that element, which incidentally you can get to easily by right-clicking Element Help for any element, and there is the help that you now see. And if I scroll down with a closed form model, you can see that there are references. The model was essentially grabbed from the literature. In addition to closed form models, we have EM models. And these models are identified with, for example, you'll see EM quasi-static, or possibly EM based, which you see right here, and there is even an FEM quasi-static. What are EM models? Well, what they do is they take the cross-section of your line, so imagine our microstrip in cross-section, and they solve the transmission line parameters with an EM simulator. It's all done behind the scenes. There's nothing you have to do to set that up. In the EM quasi-static models, we solve for the current and charge on the conductors using what is called a moment method. It's pretty fast and it's very accurate so long as your line width is greater than a skin depth. Well, is that true? Yes, if you're on a board. The skin depth of copper at 1 gigahertz is 2 microns or so, and your lines are much thicker than that. The only people that might need to worry about that assumption would be people working on silicon chips. That said, we're again going to go ahead and use our closed form model. So I come down to the emlyn, left click, and I hold the mouse button down and I drag it into the schematic and I release. So I'm not holding any mouse button now. You see I can move it around. If I right click, it rotates. If I shift right click, it flips up down. If I control right click, it flips left right. Once you have the element where you want it, click and it's placed. When you have an element placed, if you move the text, it moves by itself. If you move the element, the text moves with it. What if you want to rotate or flip after you place the model? It's easy to do. You can right click, rotate, and you'll notice the cursor's turned into an angle symbol. If I hold down the left mouse button and pull it out, and I start rotating, notice that the element rotates about the origin of the arc. So it's really a rotate and move. If you want to flip, right click. You can flip the element and you draw the axis about which it flips, either horizontally or vertically. Well, we need a couple more elements here. We need another emlyn. One simple way to get this, if you already have one, is to copy and paste it. So in standard Microsoft manner, I select, left mouse click, Control C for copy, Control V for paste. It's been put into the buffer, and there you are. We have another element. Now to finish our circuit, I'm going to need a T-junction between these two lines and then a stub hanging off the T. At this point, to get the T, I could run it back over to my elements to junctions and get it. I'm going to show you a different way though. I'm in the schematic and I type Control L. And this menu comes up. And this is all the built-in elements in the software. Now, you can either search by their name or their description. And notice where my cursor is now, the little upside-down triangle or funnel. Things are ready to search on names. You probably don't know the name of the element, so maybe you want to search on description. Hold down your Control key, click on the column, the funnel or triangle is by description. I go down to the bottom here and I type, for example, microstrip space T, and there you go. These are all the built-in T models in the software. Now, why so many and what their difference? Okay, first of all, they can either be closed form or EM based. We're going to use a closed form model. Also notice some of them, like this one I just clicked on, has a $sign at the end of it. And what this does is it allows the T-junction to get its values from its neighbors. That way, you don't have to type in the numbers, and we'll see this. So it's very nice to use $ elements. Some of the elements have an X in them at the end. An X is an X model, and what an X model is it actually uses tables that we derived in the laboratory from EM simulation. The advantage of these models is they're fast because they're table-based, and yet they're EM accurate. So again, in general, X models are highly recommended to use. That said, we're not going to use one. We're going to just use the MT $. I hit OK, and you can see my T-junction is ready to be brought in, and I go ahead and wire it up. Notice here the green dots. Green is good. It means it's wired. If you move the T away, you will see the red wires. Control Z to undo. If you wish to move it away and have it unwire, hold down your Control key and it will not wire. Incidentally, you can, of course, always draw wires at any point by going to an X, as I'm doing now, drawing to the next X, and a wire is drawn, if you wish. I'm going to Control Z here and bring the T back. The final element I want, other than ports, is a stub, and again, I could either go find it, it's called an MLEF, or I could Control L and get it that way. I'll show you another way. I take the MLIN, Control C, Control V, bring it down here, and since I know the name of the other element, for MLIN, I type MLEF, and there you go. We turn the MLIN into an MLEF. You can turn any element into any other element. We could actually change this to a FET if we wanted to, FET. One word of warning on that, though. When you change an MLIN to a FET, there are a lot of parameters that a FET has that an MLIN doesn't. And so it's going to use defaults. So be sure to check those various parameters when you make that big a change. Let's go ahead and rotate our MLEF here and bring it in, connect it up. Green dot is good, and there you are. We're ready to go. The final thing I need are 2 ports. We could go find them under ports. An easier way is to either use the toolbars up on top. For example, here's the port. Or what I like to do is type Control P, built-in hotkey for ports, Control P, double right click to double rotate, and our circuit is finished.